Welcome to this explainer, everyone. Now, if you're tuning in today, it tells me something about you. It means you aren't just here to passively absorb a bunch of facts, right? No, you're here to master the actual architecture of problem solving itself. Today, we're unpacking a really fascinating framework that focuses entirely on algorithmic planning. So I want you to think of this not just as a standard review of technical concepts, but as a high-level strategic briefing for your mind. Okay, let's dive into this. We're going to explore the exact concepts designed to turn you from a passive observer of complex problems into an active strategic architect who can completely dismantle them.
Seriously, how do you solve the unsolvable? Think about it for a second. Whether we're talking about navigating a Mars rover across some jagged alien crater, optimizing a massive global supply chain, or scheduling a complex project across dozens of different teams, man, the initial scope of these challenges can feel entirely overwhelming, literally impossible, right? But, as you know, in the realm of computer science and algorithmic design, we don't rely on panic, and we certainly don't rely on brute force. We rely on a highly structured mission. We rely on planning. When a machine is faced with a chaotic, seemingly impossible objective, it needs a very specific set of instructions to find a path forward. And well, that is exactly the journey we're embarking on today.
So, the crucial point is deceptively simple. The fundamental secret to tackling literally any massive undertaking comes down to three basic steps. Step 1, apply your foundational planning knowledge. Step 2, decompose the problem. And step 3, solve those resulting subproblems. Let's pause on that word for a second. Decompose. That word is doing a ton of heavy lifting for us here. Because you never solve a massive, complex algorithm all at once. Think back to our Mars rover. You don't just write a program that says, explore the planet and call it a day. Obviously not. You shatter that monumental task. You decompose it. You check the battery, you rotate the wheels, you drive 3 feet to the left, you analyze the specific rock. Once you've solved those individual micro-challenges, boom, you've essentially built the stepping stones to cross the entire crater. It's an absolutely crucial cognitive shift you have to make when designing algorithms.
All right, so now that we've got a handle on the overarching philosophy, breaking the massive down into the microscopic, we really need to talk about the actual mechanics of it all. Like, how do we actually execute this decomposition? Because you can't just walk onto the battlefield of complex computer science without the right equipment. So consider this your strategic arsenal for algorithmic warfare. This is your personal planning toolkit.
Now, what's really interesting about this slide is the sheer variety of methods you have at your disposal. Each of these represents a totally different way a computer can actually think about a problem. So, first up, we have the foundational planning problem itself. This is all about defining the start state, say, the rover sitting safely in the lander, and the goal state, which might be that distant rocky ridge, plus the actions available to get there. Simple enough, right? Then we move to planning with state space search. This is essentially mapping out every single possible scenario and searching for the absolutely most efficient route through that map, dodging obstacles along the way. Next on the list is partial order planning, and I love this one because it's brilliant. It lets the system work on different parts of a problem in parallel. So our rover can be analyzing soil samples while simultaneously charging its solar panels, without forcing this rigid, artificial sequence until it's absolutely necessary. Make sense? Then we get to hierarchical planning. This one attacks the problem from the top down. You start with a broad, abstract plan, like navigate to the ridge, and you fill in those granular, millimeter by millimeter wheel rotations later on. And finally, conditional planning. Think of this as your what-if generator. It prepares the system to adapt on the fly, like teaching the rover exactly what to do if a Martian sandstorm suddenly rolls in out of nowhere. Honestly, it's an incredibly robust toolkit.
But hey, let's be totally honest for a second. Theory is absolutely wonderful, but an algorithm only really proves its worth when it actually runs, right? Just understanding hierarchical or conditional planning conceptually, that's only half the battle. And that's exactly why the source material explicitly includes demonstrating these planning techniques using open source tools. This is where the abstract mathematics and the high-level logic finally get their hands dirty. By diving into open source environments, you, the problem solvers, can actively test, break, and refine these models. It brings the theory to life. It ensures you aren't just memorizing dry definitions from a textbook, but you're actively observing how these logical frameworks behave in real time. This hands-on testing is exactly how we cross that bridge from pure math to real-world application.
And this brilliantly illustrates the duality of this entire subject. Take a look at this comparison. On the one hand, you have this deeply academic demand for precise problem statements and logical constraints. We're talking about analyzing causal links. It's all about deep, meticulous, rigid logic. But then, on the other hand, you have to take that strict logic and translate it into sustainable planning solutions for actual real-world problems. That's the real challenge. This framework is explicitly designed to be a bridge between those two worlds. It literally takes the deeply theoretical analysis of constraints and demands that you forge it into something sustainable, something that actually works out there in the chaotic real world.
I want to pause here just to briefly highlight the gravitas of a term we just touched on: causal link constraints. This concept is absolutely central to defining a precise problem statement. So in algorithmic planning, a causal link is basically just a rule. It's a rule that says, hey, action A has to be completed because it achieves a condition that is absolutely necessary for action B. Therefore, a constraint ensures that no other action in the system is allowed to mess with or interfere with that link. Imagine a robotic arm on a manufacturing line, right? If that arm needs to open a paint can before it can dip its brush, a causal link constraint guarantees that the arm doesn't accidentally move the can to a completely different room in between those two steps. Now, obviously, that sounds incredibly obvious to a human being, but a computer? It has to be explicitly taught this kind of logical sequencing. And this rigorous analysis of these constraints, that is exactly what leads to those sustainable, error-free real-world solutions we were just talking about.
Which brings us to what I personally consider the ultimate drop-the-mic goal of this entire framework: representing messy, real-world problems as structured planning problems. This right here is the absolute pinnacle of the problem solver's journey. Because let's face it, the real world is deeply, wildly messy. It doesn't come neatly packaged with clearly defined state spaces or perfectly organized causal links. No way. It is chaotic, it's unpredictable, and it's full of friction. So the highest level of mastery you can possibly achieve here is the ability to look at that real-world chaos, whether it's gridlock traffic, a massive logistical bottleneck, or incredibly complex resource allocation, and successfully translate that mess into the highly structured, precise language of a planning algorithm. That right there is where true innovation actually happens.
So, look at how far we've come. We've journeyed all the way from the initial overwhelm of facing an unsolvable problem, navigated through this powerful arsenal of state space and hierarchical planning, and drilled all the way down to the ultra-precise analysis of causal links. But the ultimate metric of success isn't just understanding this explainer. It's about what you actually do next. So, how will you apply this toolkit to design your own sustainable solutions? The algorithms are out there, waiting to be written. The massive, tangled problems of the real world are literally just waiting to be decomposed. The toolkit is yours now. Thank you so much for joining me today, and I really want to challenge you to go out there and start planning.